Adventures in Venture.
I can't fucking do that. Okay. I thought it was some audio thing. Do I just start? Is that what it is? Okay. Welcome to Adventures in Venture. I'm your host, Evan Maindonald, and my guest today is Dr. Jessica Wade. Dr. Jess Wade is a physicist and material scientist at Imperial College London. Her research investigates polymer organic light-emitting diodes, otherwise known as OLEDs, and her specialism is Raman spectroscopy. We'll get into what that is in just a minute. Dr. Wade began to gain profile in her 20s when she started writing Wikipedia biographies about underrepresented female and ethnic minority scientists. As her Wikipedia entries climbed into the hundreds, she began to speak and write more about gender and diversity in science. She's received a number of awards, medals and citations for her work in physics and for this work, including an honourable mention by Wikipedia co-founder Jimmy Wales. Her specific research interests include material science, chiral materials, and circular polarisation. And again, we'll get into what those things are as we speak. So, Jess, welcome to the show.
Hi, Evans. Thanks so much for having me.
Is there anything you'd like to add to what I've just said?
There's nothing I'd like to add. I maybe can go a bit deeper into what Raman is, but we can do that whenever.
No, I'm very interested. I don't know what Raman spectroscopy is. I know that some of your work is very interesting, or the work that you've told me about is very interesting. But yeah, I'd be really interested to know. So please tell us.
Yeah, I guess most people are more familiar with ramen noodles, and then Raman spectroscopy is a vibrational spectroscopy based on a molecule's polarizability. So basically how much you can move the electrons within a molecule around. And vibrational spectroscopy means exactly that. It means that you give the bonds in the molecule, so the bonds between atoms, some energy to start vibrating. And then we basically study those vibrations. And it's an incredibly useful technique. It basically involves kind of shining a laser on a material. So that could be a powder of a new material that we want to use to make an OLED, an organic light emitting diode. It could be the thin film that we're using to generate electricity in something like a solar cell. And you basically shine a laser on those materials. You make all of the bonds within those materials start to stretch and vibrate. And when they do that stretching, they kind of scatter the light from the laser back. So shine laser down, scatter the light back. We collect that scattered light. And in that scattered light, you get a kind of pattern, which is your Raman spectrum. And that has lots of peaks that correspond to the different bonds within that molecule. And so you actually get this kind of chemical fingerprint of exactly what's inside that material, that molecule, that structure, which is incredibly rich information for physicists and material scientists like me. There have been some proposals to use Raman in kind of airports, so you could scan a liquid and instantly tell exactly what's in that liquid. But how we use it is to try and understand exactly how the bonds are arranged within that material system to make them more or less ordered, or to make those materials interact with other materials, to mix things together, to get better properties for an electronic device. So it's this kind of very powerful characterization technique, all based on the interaction of light and materials, which I find really fascinating. And kind of an extra fun fact about Raman was it was developed by the Indian Nobel laureate C.V. Raman, who was a sensational physicist who was actually classically trained in Indian stringed music. And it was his kind of observations of vibrations on Indian stringed instruments that led him to propose this Raman scattering technique of vibrations within molecular structures, which I just think is so great that you have this kind of crossover between music and really hard applied physics.
That's interesting, isn't it? Because, I guess in physics, it is to some extent, not all about vibration, but, there is, we detect what things do via vibration. I'm interested to know, are there limits to what you can achieve in terms of detection of type of materials with Raman spectroscopy? And is it superior to other methods of remotely detecting things by kind of, shining something on them?
Yeah, I mean, the different techniques are kind of lend themselves to different applications. So Raman's particularly good for materials that are polarizable. So where you can move these kind of electrons around, where you can distort. If you imagine your kind of molecule and you've got atoms, and the atoms have these clouds of electrons around them, when you can distort that electron cloud, that's what Raman's really good for. If you have something like infrared, so infrared is another vibrational spectroscopy, and that will lend itself to different types of molecules and materials. And then you'll have some materials that actually are really good at absorbing or emitting light. So they've got really strong electronic transitions. And then we might use a more simple spectroscopy like absorption or photoluminescence. So you have basically, I mean, so I work in this really fascinating intersection of physics and material science. And I think exactly right now at this point in time, we've got phenomenally good at designing better materials for new technologies. But we've also got all of these new characterization techniques coming online, getting more advanced and getting more mature. They give us kind of unparalleled opportunity to understand and optimize those materials. So you have this really great chance for innovation because you're saying we can do things we've never done before from synthesis, and we can do things we have never done before from understanding. So let's bring that together to design the kind of best material for the future.
So I referred in my introduction to three terms: chiral materials, circular polarization, and chiro-optical technologies. Could you explain what those three are? And also, while you're doing it, if you could maybe just touch on where Raman spectroscopy can be useful in those fields.
Yeah, I guess, I mean, the kind of intersection to bring up the point that you made before about this kind of understanding and the detection limits you can get to with light and light matter interactions and exploiting them. Chiral light, circularly polarized light, is one of the polarization states of light. So I guess first we'll step back and think about what chirality is. Chiral objects exist as a pair of non-superimposable mirror images, like your left and your right hand. So we see chirality at lots of different length scales in the human-made and the naturally occurring world. We see chirality in things like electrons and photons, so at the subatomic scale. We see chirality in molecules, so in things like DNA and peptides, they have this left-handed or this right-handed twist. Actually, all DNA on planet Earth is right-handed, all proteins are left-handed, which is pretty zany. And then we see chirality in bigger objects like shells and in the plants of the barks of some plants and in things like galaxies, spiral galaxies. So we see these kind of clockwise, anti-clockwise, left, right-handed patterns a lot throughout nature. And the way we're thinking about it, particularly this term chiroptical or circularly polarized, is how can we take that chirality that we see in light at this subatomic scale, that we can have left and right-handed light, clockwise and anti-clockwise light, and use those phenomena for a technology. Now, it turns out, the light that probably most listeners are familiar with is unpolarized light. If they've got kind of fancy sunglasses, polarization-sensitive sunglasses, then they're usually linearly polarized. So they block out one component of polarization, which you can kind of imagine as a light wave just oscillating in one plane. So if you imagine your kind of nice picture of what a wave is, and you draw that wiggle going on one plane, then that's a linearly polarized light wave. And we think of light as being vertically or horizontally polarized, that kind of comprises linearly polarized light. Now circularly polarized light is a little bit more exciting, because instead of the electric field tracing out that kind of oscillating wave that moves towards you vertically or horizontally, in circularly polarized light, it traces out a corkscrew as it moves towards you. So it traces out a clockwise or an anti-clockwise corkscrew as light propagates towards you. And that's really cool. I mean, we see actually circularly polarized light quite a lot in nature. We see circularly polarized light reflected to us from the shells of some beetles. And we know that mantis shrimp can differentiate left and right-handed light with their eyes. Humans can't differentiate left and right-handed light with their eyes, but we can think about using it to make new technologies. So we can use it actually to make more efficient OLEDs due to a particular manifestation of chiroptical phenomena. That is, to minimize glare in a smartphone display or a television display, manufacturers put a circularly polarized filter there, which is very clever as an anti-glare filter, but not very clever at maximizing the light coming out of the pixels of your phone.
Okay, so I'm familiar with polarization, but are you saying that, so light, depending on how it's polarized, is either left or right-handed? Is there a version of it that's neither-handed?
If you have 50% left-handed light and 50% right-handed light, then it's unpolarized light.
Right. And when you polarize it, essentially you're saying that it ends up spinning in one direction or the other. Is that right?
The electric field will rotate in one direction. It will rotate clockwise or anti-clockwise. Right.
And so you can kind of harness that to I don't quite understand the connection between how you can harness that to reduce glare. The sort of it doesn't quite click in my head. But
well, maybe I went too many steps forward. If you imagine a OLED display, if you imagine the pixels of your mobile phone, or if you imagine what happens in the kind of stack of your, if you imagine a cross section of your mobile phone display, you have basically an electrode where you inject charges. You've got some interlayers, which will make it easier for those charges to move across. You've got something called your active layer, where you have kind of electrodes either side of your active layer. So you have a sandwich where you've got electrodes either side of your active layer. You've got your active layer. We call that active layer an active layer because that's the part that will emit light. So in a cross section of a phone, you've got sandwich structure, electrode, active layer in the middle. And basically what happens when you try and get those pixels to turn on is you inject an electron from one side and a hole from the other side. So kind of plus and a minus charge. They travel through that active layer. At some point in that active layer, they recombine. And when they recombine, they emit light. And that's the kind of radiative recombination process that happens to emit light in a television or a mobile phone display. What display manufacturers do to minimize glare is they put a circularly polarized filter on one side, so next to the glass, which will be, the light emitting interface of your device. And that filter turns unpolarized light from behind you into circularly polarized light that then moves through the sandwich of your device. When circularly polarized light hits that back electrode, which is shiny like a mirror, the handedness inverts. So if you have left-handed light hitting a mirror, it becomes right-handed. So you've now got right-handed light moving back through your device. That then hits your anti-glare filter and can't get out.
Right.
So you kind of trap the glare in the active layer by turning it from unpolarized light to circularly polarized light. And that's really effective. It means you can be outside on a really sunny day and send a text message. It means you can watch TV with a light on behind you and not be impacted by glare. But it means that the pixels in your phone or the light emitters are generally emitting unpolarized light. So you lose half of that brightness to that anti-glare filter. So at Imperial, we've been working a long time on trying to make those pixels emit circularly polarized light.
Right. And you've succeeded in doing that?
Yeah, it's pretty easy to do, actually. You need to... So before I told you about vibrational energy levels and vibrational transitions, which we can probe with Raman, there's also electronic transitions. And actually, there's also kind of charges don't only move vertically during one of these transitions, but they can also rotate. And so when you get molecules that are chiral, so this kind of handedness within a molecular structure now, not at the subatomic scale, actually charges rotate as they move between the ground and the excited state or the excited and the ground state. And it's that rotation of charges that generates this circularly polarized emission. So you've just got to work with a clever chemist who can design some beautiful molecules that can make that process possible. And luckily, we've got a lot of them around.
Yeah, yeah, good. Okay, so I think that's circular polarization. Have we covered chiral materials? Not sure.
So I think I've spoken about what kind of chirality is. So chirality, we see it in things like DNA and peptides. I guess the more interesting thing for us in the kind of functional materials community is thinking, how can we introduce chirality to materials that are relevant for technologies? So how can we think about making a molecule that could emit light chiral? Or how can we think about making a molecule that could transport electricity chiral? And why might that be useful? And actually, there are some really, really clever molecular designs where you can think about either changing the shape of the molecule. So there you take a molecular structure and you might try and make it into like a twisted structure. So I work a lot with molecules that look like springs. They can't sit flat on a plane. They kind of trace upwards or downwards like a coil. And then you just get this huge capability of thinking about really tweaking that twist of the light that comes out of them based on the shape of the molecule. So you can induce kind of clockwise and anti-clockwise twists. Or you can create a chiral structure. So you can assemble molecules that start off achiral. You can assemble them into some kind of chiral material system. So you get a non-chiral building block, and then you create some long-range chiral structure. And in that, you can imagine light becoming twisted as it propagates through it, or electrons becoming spin polarized as they move through it.
Okay, so in a sense, chiral optical technologies kind of summarizes the use of chiral materials to actually produce that circular polarization and kind of create technologies that leverage the effect that those materials are able to produce.
Yeah, exactly. It's producing and detecting secular polarization. I suppose that's it. That actually, the emission side is mainly what I've spoken about, that these are really good at making OLEDs or LEDs in general that emit secularly polarized light. But actually also detecting secularly polarized light is really useful. Because if you wanted to encrypt data transfer where you were using light to send information, then you could have a secularly polarized detector. Or if you wanted to just double the data transfer rate, so make use of a left and right-handed channel, you'd have a detector for left and right-handed light. So we're interested in technologies that both emit and detect secularly polarized light.
Okay, that's interesting. I mean, could that be used as a sort of in the same way that a private key is used as an encryption for digital signals? Or am I?
I think it absolutely could be. I think that the interesting thing about secularly polarized light is that eyes can't differentiate it. So unless you've told the receiver to expect secularly polarized light, you wouldn't be able to tell that your signal was secularly polarized. So you'd have to have a secularly polarized pump, signal generator, and a secularly polarized detector. But you can also imagine, I've got great friends in Durham who create kind of security inks, so features that you might put onto some kind of important product or whatever system it is that you're creating, where you pattern something with something that will absorb or reflect secularly polarized light, and it kind of adds an extra level of security to a hologram or something like that.
Yeah, okay, interesting. And when you were talking about chiral materials, one thing that immediately occurred to me is the kind of fractal patterns that you see in nature. I mean, is there a connection between those two things, or is that a...
I don't know. I mean, lots of them have these. When you turn these molecules or these powders that chemists generate into thin films, lots of them form these absolutely beautiful structures when you put them under a microscope. In general, the more beautiful and complicated a structure is when you look at it in a thin film, the more difficult it is to put into a technology, because you can imagine within that structure, there's a lot of variations. It's quite anisotropic. If you imagine injecting electricity into it, nothing wants to move very consistently. Or if you imagine it emitting light, it wants to emit light from particular crystal areas.
So could you just explain that term, anisotropic?
Yeah, so if you imagine something like you mentioned the word polymer actually in your introduction. If you imagine something like a plastic or a polymer, in general, if we process them into a thin film, so if we made a thin film of a plastic, and we're actually quite good in the UK at making these light-emitting plastic materials. If you imagine doing that, then you've usually got quite a disordered system. So you have lots and lots of disorder, no preferential direction for any light to be emitted from or into. You've got this kind of disordered system. It would absorb light the same in all directions, and it would emit light the same in all directions. If you have something instead, like a small molecule, particularly where you've tried to introduce some kind of ordering, so you've tried to assemble them in this particular chiral structure, there you no longer have this kind of uniform distribution or emission or absorption of light. Actually, it happens in particular directions. And anisotropy is saying to you that you've got this directional component of light emission or absorption or electron transmission. So anisotropic systems, it will depend whether you're looking along one axis or the other axis. How the function will depend on the axis they're looking along. Okay,
and I mean, would you apply that to light? In other words, the circular polarization of light, or is that a term you'd apply to materials?
I think you'd think about it. I mean, you can have anisotropic functional properties, so that would be a light matter interaction that's anisotropic would certainly be something that we could apply it. But you can have, I guess it's a nuance about the way you'd phrase it, but, anisotropic packing, directional packing of a molecule, and then that impacts the functional properties. I think that's kind of the interesting thing about the systems we work with, is that you think about the design of the molecule at one length scale, then they assemble into this material system, and that could have different interactions than just what you're looking at in the molecule, like different functional properties. And then you consider the functional properties of the material, and then you'll put that into a device. So say you had some system where you knew that your molecules had this twisted structure, you could assemble it into this kind of columnar arrangement of all of these twists coming together. Then if you take that column, how you orient that column when you think about a device, do you want those columns kind of standing up and in the direction that the light's going in or coming out? Or do you want those columns lying down and perpendicular to that direction? and how that then impacts the functional properties is just a fascinating question for someone like me. And then thinking about how you'd work with someone who's trying to think about a technology and say, hey, we want to get the best charge transport possible, or we want to be so efficient at absorbing light so we can generate this amount of electricity. That's the kind of phase space that we work in terms of, you know, these types of kind of considerations that you take when you're developing some kind of new system. And that's why we turn to spectroscopies like Raman spectroscopy, because you really want to be able to understand at a molecular level what's going on. But we can't look at these molecules using a microscope because they're just much too small to do that. So we have to turn to light to get that information and look at how they interact with light.
Okay, that is interesting. Okay, so I would like to talk more about the work that you've done in materials development, and particularly the stuff, you know, as it leads to, I guess, potential for commercialization of technologies. But before we get onto that, I understand you've also worked on technologies that can potentially enable room temperature solutions for quantum computing. And I don't know whether that's actually tied up with the work that you're doing in materials science or not, and the things that we've just discussed. But could you talk a little bit more about that and its potential importance?
Yeah, I suppose kind of quantum technologies are capturing huge interest, and probably lots of the listenership of this kind of podcast interest. They're something that could enable a huge number of diverse applications. So really, any technologies that exploit quantum phenomena to employ or to advance some new functionality into that particular device. So for quantum sensing, you can invoke the quantum phenomena of your particular materials platform to get much higher resolution sensing of whatever it is you're trying to monitor. So you can monitor for incredibly weak magnetic fields, or you can have very high spatial and temporal resolution to way that you're detecting fields, whether they be magnetic or electric. So you have kind of quantum sensing that invokes this interaction of fields or of whatever with a molecule or a material, and you monitor those interactions with extraordinary sensitivity. So the kind of quantum aspect of that is just boosting the sensitivity, giving you higher spatial and temporal resolution. In quantum computing, when you step away from these kind of binary 1 and 2 state systems, well, you're kind of 0-1 state system, and go to systems where you have this huge capability to do very complex operations, with actually, you know, anything between a 0 and a 1, you have that kind of huge phase space in which you can perform your quantum calculation. Then actually you unlock completely new capabilities. So quantum sensing gives you enhanced sensitivity, enhanced resolution. Quantum computing gives you the potential to do computational problems like optimization problems. So that could be trying to design better systems for navigating cities. It could be, you know, I put in my home address and where I want to get to, and it will really quickly scope through all of those different possibilities and identify the best route possible to get there. It could be, you know, imagine that being used and applied to shipping, or it could be used to search through a whole materials landscape, like you're trying to come up with some new pharmaceutical design or some new material for a solar panel, and a quantum computer with this huge phase space in which it can perform these problems and perform these calculations in parallel to one another, and will rapidly accelerate the rate at which we can get there. So you have these technologies, and then quantum imaging actually is very similar to quantum sensing, but not kind of detecting fields, but actually just extraordinarily high sensitivity imaging. So in these cases, quantum unlocks new functionality, and gives you the ability to what we've done with conventional technologies, kind of classical technologies, in a completely different, a completely fundamentally new breakthrough transformative level. And I suppose it's capturing everyone's attention and excitement because it's taking concepts from physics, which have been well known and understood for quite a long time. But they're now saying, actually, we've now got the precision to engineer these phenomena into materials, and to think about how we can design the materials that will underpin a new generation of technologies that exploit those phenomena. And so what we're really interested in at Imperial is thinking about what will the kind of headline material systems be that will carry these quantum phenomena. How can we manipulate quantum phenomena most effectively and optimize the material system for it? Now, I think most people who are vaguely aware of quantum technologies or thinking about it, or maybe even potentially investing in it, are thinking about superconducting platforms for quantum technologies. So these are these very exciting materials that show kind of superconductivity. So as you go down below a certain temperature, usually an incredibly cold temperature, they have absolutely zero resistance, and they actually do kind of zany things like they expel magnetic fields. So there's really beautiful demonstrations of superconductors below this particular temperature where they can actually, they expel magnetic fields and they can kind of levitate small magnets when they get cold enough. But anyway, superconductors are a really exciting materials platform for quantum computers, which have received a huge amount of commercial interest. But they have absolutely horrific operating requirements. Like you have to keep them cryogenically cool. You have to completely isolate your qubit from every other qubit, because the interactions between different qubits can destroy the quantum states that you're trying to use to do your calculation. And so when you see these qubit systems built around superconductors, and you have this absolutely gigantic infrastructure that's kind of cryogenically cooling and environmentally isolating your qubits. And that not only has huge kind of environmental implications, which are obviously terrible, but actually it's just not a very efficient way of engineering or thinking about building something where you might want to have 100,000 qubits, right? Like we're not going to build a quantum computer through that.
Well, you're certainly not going to put one on your desktop, are you?
Well, I think actually the argument back would be you'll never have one of these on your desktop. That's not what these kind of technologies are for. You may have a quantum sensor that you use in a hospital, because actually that resolution, that sensitivity from something like magnetic field sensing is really great for brain imaging. And there you could fully justify having a quantum sensing system. And actually there's some really exciting work doing this in coming out of Nottingham University. But I think that, will we all have a quantum computer? No. Will we maybe use some kind of cloud architecture for quantum computing? Probably. Will the banks and the governmental institutions that we're part of and involved with use them? Yeah, then yeah, 100%. They'll use them for something. But will we have one? No. Is it sustainable to do it with superconductors? No. But could you do it with a different materials platform, like a molecule, and exploit kind of those electron spins that we were talking about before, these polarization states of electrons? That could be your two-level system under which you do your kind of entanglement or your superposition to generate these kind of quantum states that you want to do your calculations with. And actually molecules would allow you to do that at room temperature with extraordinary tunability that comes from their chemical structure. So if we got the molecular design right and worked out how we turn those molecules into something that could sit on a substrate in an appropriate way, then yeah, I think molecules hold huge promise for sensing and computing in quantum.
Okay, well, that's super interesting. I just want to take you back a little bit. You used a phrase a couple of times, which is phase space. And what I wanted to do is just kind of clarify my understanding of what that means. I do understand that, traditional computers run on binary, and that quantum computers are run on qubits, which I think is effectively a system of, is it 0 to 64? Is it more than that per bit?
No, I guess it's much more. It's not 0 to 64. You kind of have if you imagine your kind of classical demonstration of 0 and 1, computation on a quantum computer would produce some kind of superposition of all of those 0 and 1s. So you have your like 0 and 1 in your axes, and then the quantum space in which you could do your calculation is everywhere between that.
So it's essentially analog. I mean, it could be anywhere between 0 and 1, or is it uncertain where it is? Is that the point?
Yeah, you're uncertain where it is. You basically measure the system before you do the calculation. It does its calculation, and then you measure it afterwards. And in between that, you don't know where it is. It's only when you measure it that it collapses into one of these zeros or ones.
So how is that uncertainty actually harnessed to produce a computation? And I am aware that this is more similar to the way that humans think than the way that computers work, or the human brain works, or at least that's what I've heard or read. But I'm really just trying to get to the guts of how that connection occurs.
Where you've heard it or read it is the way that's more similar to how human brain works is something called neuromorphic computing. So that's the one that's much more similar to human brain like, and that relies on the contributions of many signals to the way that our brains interact with our neurons in our brains interact. You kind of fire these action potentials, and once the sequence, the build-up of those action potentials get larger, it triggers the next system. And that's this neuromorphic type logic for computing, which I'm not sophisticated enough to talk to you about, but I know it's an incredibly efficient way of doing computation. Quantum computing, you develop algorithms and kind of logic gates that will exploit the fact that you can perform calculations while you're in this superposition of 0 and 1s. So you can do your calculations while you're in that superposition of states, and then have access to all of those states in your superposition. And only when your calculation has finished or you read it out will you go back down to something that you can measure. So you kind of exploit that space between 0s and 1s and to do your calculation in, and then you measure it afterwards. And you'd get to doing that by designing a good algorithm or designing a good kind of logic circuit to be able to test it, or that would have those in.
Does it mean that there are actually an infinite number of possible outcomes?
Well, the outcome will always be 0 and 1. The outcome will, the thing you measure will be 0 and 1. There's an infinite number of possible routes, and that's why it's so good for route optimization. There's an infinite number of possible ways that the calculation could be done.
Okay, yeah, right. So yeah, the outcome can only be one thing or another, but there's an infinite number of ways you could possibly get there.
Yeah, exactly.
And just when you talk about entanglement, how does that come into the picture?
So you can do quantum computation either with light or electrons. You can have you can have it based on spins. So electrons would be based on the spins, and you can also entangle light. So a quantum computer would use entangled qubits. So you'd generate your qubits, you'd entangle their information, and then it would be that entangled state that does the calculation. You generate that entangled state by producing, say you produce 2 photons, you produce them at the same time, you produce a pair of photons, and actually that notion of that process of producing that pair of photons means that they always remember what's happening to the other one. So it doesn't matter if you separate them over immensely long distances. If you've produced that entangled pair, your up photon will always remember that the down photon's nearby, and that it's entangled with that down photon. So it's that kind of connection between them.
Is it a matter-antimatter pair? Is that what we're talking about here, or not?
It's
negative, positively charged, or
it's not like that, because it's more about, it's spin up or spin down electron. It's about angular momentum rather than
it's about the direction of spin.
Charge.
Okay, yeah, okay.
Yeah. So it's a quantum state. They always remember the quantum state of the other one.
Right. Even though they're separated and can be separated by quite a long distance.
Very long distances. So when you measure one of them, you always know what's happening to the other one, which is why they're so good. Why entangled states are so good for using for encryption, because you can encode information. You know whether your message has been intercepted, and because you know what you should be measuring by measuring one of the other ones.
Okay.
It kind of gives you more opportunity for doing parallel computations and kind of interconnected processing.
Right. Okay. All right. So let's just jumping back to the kind of material science side of things. We talked about superconductivity and the fact that quantum computers at the moment are, I guess, to some extent constrained by the fact that they need to operate in these low temperature environments. What is the current state of play with material science in terms of actually finding room temperature solutions to perform those kind of and also, sorry, let me just add a little piece onto this as well. Is it likely that those solutions will perform at anywhere near a similar level to the current quantum computing solutions?
Well, I guess this comes down to a problem of investment, that you kind of have a lot of investment going into superconductors at the moment, and investment obviously drives and unlocks innovation. If you have a lot of people working on superconductors, there's unrivaled opportunity for building infrastructure around superconductors. And actually, I've heard some people say it doesn't really matter about the energy demands. It doesn't matter if they're environmentally terrible, because the economic breakthrough you'd get by building an effective working quantum computer is worth it. So it's kind of like let's just go fast and loose and see what we can do. But actually, if you had comparable investment into different, more high risk, high reward materials platforms, like let's build a molecular quantum processor. Right now, the technology is nowhere near the TRL that you need for actually building a quantum processor, and it's not ready for doing anything like where superconductors are. But that's just because it hasn't had the investment. If you take what's happening in the UK quantum community, there's very few chemists involved, whereas we could involve far more chemists who design better molecules, who then we work together to implement them or translate them into a particular quantum computer. So I think the challenges that we have at the moment are just that we don't have enough or equal money going into the different materials platforms. But like I said, you've got options to do it in solid state, so in kind of spins in the solid state, or you can do quantum computation with photons, so you can do it with light. Superconductors would be more kind of solid state systems, whereas if you did it photonically, like they do at PsiQuantum or anything like that, that's using light. You still have to cryogenically cool your detectors, so you have kind of single photon sources, and that's where you generate your entangled pairs of photons, and then you have your single photon detectors to read out the signal, and they still have to be cryogenically cooled to get the sensitivity that you need. So there's still some materials challenges associated with that, even if you're using light. But in general, they're considered much more efficient, I think, than solid state systems at the moment. But there are other platforms, there's topological systems where you can bind the quantum state, or the quantum state is bound to the surfaces, which kind of protects them from losing their kind of coherence or losing their quantum state. You can have 2D materials, you can have defects in wide bandgap materials, you can have molecules. So there's lots of different materials platforms. And we're at a really exciting stage of technology development where people are really exploring that whole materials landscape. But because you do have this big commercial focus from some of the really big companies that have put a lot of money into superconductors, and that seems to really drive where I think big investment goes, where there are some really exciting kind of early days technologies and that have huge potential and just not the same amount of funding.
Yeah, but I think therein lies the opportunity to some extent. I mean, and, from an investor's perspective, looking at where the frontiers are of this technology are going, and saying, actually, is there a better way to do something that we're already doing, or is there a more efficient way to do something that we're already doing, because you don't need this huge cryogenic cooling infrastructure? I mean, that to me is where the opportunity for innovation and investment lies.
Yeah, I think I'll just jump in and say the kind of interesting things in all of these systems often happens at the interface between platforms. So when you have kind of hybrid classical quantum platforms for sensing, then you benefit from the classical capabilities and the advantage that brings, as well as the quantum aspects. I know that's really great in magnetometry, for example, or navigation systems. Whereas in computing, actually, if you took some kind of technology like a mature platform, like a superconducting qubit, and you can do clever kind of nanofabrication so that you can actually simultaneously grow a molecular system on top, and then you get protected quantum processing, you get kind of protected states from your molecules, and then you get your well understood quantum processes from your superconductor. So you can kind of benefit from both materials platforms and regimes, and that kind of disruptive thinking and ways of understanding a molecule and actually having these multiple energy levels within a molecule that we kind of touched on in the beginning with these rotational and vibrational states. Those multiple energy levels let you encode some kind of protection onto the system that you might be doing your kind of quantum operation in. And then I think you get to really exciting spaces that, really in that deep tech landscape of needing quite a lot of investments to become something tangible, but actually have huge opportunity to bring a real step change to the kind of environmental sustainability of some of these quantum devices.
Yeah, well, I mean, technological development is, to some extent or other, all about disruption of existing systems and existing processes and doing something in a different or a better way. So I think, one of the reasons that I do this podcast is to better develop my understanding of these technologies and things that are coming along, so that I can be ready to identify and jump on investment opportunities when they arise. So yeah, I mean, this stuff is quite interesting stuff, and I also think there's a kind of a commercial aspect to this, in the sense that if there are areas of research that are really promising, but they just aren't receiving enough investment. And the question has to be asked: well, how do you unlock that? How do you sort of push through from opportunity to commercialization? And I guess we can touch on that.
I think that's true. I think it's the unlocking of the opportunity from a materials perspective, and then also the kind of characterization that we spoke about before, that actually to really understand why these qubits or these quantum sensing systems are working better or worse than other ones, we have to really, really better get a grip on how we characterize them and define them. And at the moment, we're not kind of sharing that infrastructure well enough, or we're not sharing those ideas well enough. And that's where I think there's huge opportunity for innovation as well. Like, superconducting qubits, no one's really nailed the way that you fabricate them. So if you make an aluminium qubit, which is often what they use for superconducting qubits, almost every time you make one, it behaves a little bit differently to the other time you've made it. The kind of lifetime in which you can perform your quantum algorithm is slightly different. They're not exactly reproducible or reliable, which makes it impossible to imagine building a quantum computer where you can imagine that you want them all exactly the same. You want all of your qubits to be the same in the quantum processor that you're making. And part of that is because the people who are making them don't really understand how to characterize them while they're operating, this kind of in operando characterization. So while you're driving them, how do you characterize their materials properties so that you know how to better fabricate them? So there's a real opportunity for innovation in that characterization space, which I think is really cool. And it just means you have to have the right people in the room, the engineers, the physicists, everyone coming together to ask the right questions to deliver on it.
I understand that you're involved in some initiatives which are around getting physicists working better with engineers to actually bring some of these technologies to fruition, to market. Can you talk a little bit about that?
Yeah, I work at this incredibly interdisciplinary and kind of diverse university of people from all different engineering disciplines, but also natural sciences, and also the business school, and also medicine. And quantum kind of directly impacts all of those different areas. So you can have people in engineering working on the electronic engineering or the mechanical engineering to support quantum technologies. You can have people in medicine thinking about how you'd apply a quantum sensor to diagnostics or monitoring. You can have people in the business school thinking about how you develop some kind of business case study for a quantum company. You can have people in maths and computing thinking about deploying and developing quantum algorithms. So really quantum directly links all aspects of our university in this really exciting way. And actually we have this Center for Quantum Engineering, Science and Technology called Quest, which links everyone kind of with no physical home, but we come together and we kind of take on these big challenges and bring together teams of people. We're thinking a lot about how our curriculum at the moment supports students to be the kind of next generation of innovators in quantum technology. So how do we get all engineering students to have a general appreciation of quantum so that they can start to think about how they'd, design a better dilution fridge or do better circuitry that can interface between these classical and quantum components? Like, I think a lot of what is happening in the UK and the global quantum sector is that we have a huge shortage of engineering skills going in. We have enough of the quantum experts. We have enough of the physics graduates who are coming up with the fundamental concepts to drive these technologies, but we don't have enough of the engineers who are going to really make that happen. And so at Imperial, we're trying to link it kind of, very much from the start to say, actually, if you want to put your quantum sensor onto a bridge to enable, whatever, a more efficient transport network, you're going to have to speak to the civil engineers early on about what kind of structure or system it might have to be able to withstand, and the types of ways that they're collecting that data and information at the moment. So we're really trying to bring those communities together to have those conversations really early in the innovation journey. And also to better equip our scientists and engineers of the future so that they're ready to have really transformative and impactful careers.
Yeah, it's interesting. When most people talk about quantum, they think about quantum computing, but actually, there's a whole series of aspects to quantum technology that actually are exploitable in different ways and touch on all sorts of kind of areas of business and science, which I think is an interesting thing for me that's come out of this conversation. Can we talk a little bit about materials with enhanced conductivity and how they open up possibilities or new possibilities for electronic devices? And also, I'm interested in the work that you've done with polymer-based OLEDs and how they're unique in the realm of lighting technology? That's a sort of a fairly broad question. Do you want to just pick out whichever bits of that might be most interesting?
I suppose we touched on it in the beginning when I was talking about Raman. I mean, so lots of the UK actually has been real pioneer in developing these printed electronic materials, so carbon-based semiconductors. So semiconductors that have the semiconducting properties of something like silicon, but have processing properties of polymers. And generally, they're kind of based on these conjugated carbon structures, so alternating single double bonds of carbon. And actually, you can design them as small molecules, so you can make things like linear fused ring structures of something called benzene, but you can join them together to make something called pentacene, which is 5 of those benzene rings joined up. You can make kind of football-shaped small molecules called fullerenes, which we use in photovoltaics, or you can make long chains of these conjugated systems called polymers, where you have kind of repeat units of a particular molecular design, and you repeat them, ad infinitum, depending on how long your polymer chain is. What's really exciting about these carbon-based semiconductors is you can tune their electronic and their optical properties with their chemistry. So much like the molecules you might use for a quantum application, if you're trying to make a light emitter or a light absorber, something for an OLED or a photovoltaic, you can change their chemistry to tune where spectrally they'd absorb or emit, so what color they absorb or what color they emit. And you get kind of huge increased functionality that you can kind of take these semiconducting inks and then print them onto a plastic to make some kind of flexible or conformable photovoltaic or roll-up display or something like that. So they have huge potential in low resource environments where you might want to do something like print out a solar cell and then roll it out as kind of a massive sheet to generate electricity off-grid.
That's interesting. So I mean, could the same material potentially both absorb and emit light? And could you actually integrate that somehow into a plastic? And I'm thinking about 3D printed structures here.
I think you would have. I mean, obviously they'd absorb and emit light at different wavelengths, or else it would be pretty rubbish because it would be absorbing all the light that it emits. I think you could have a system. Probably the most effective way of doing that would be to have some kind of system where you have 2 layers within your device, and that you can drive it with a voltage that you apply to one of the layers that emits light, and then one of the layers that absorbs light, and they're pretty much transparent otherwise. I think that would be kind of easy to engineer, like a bi-layer device. I think actually if you wanted to, in general, things that are really good at absorbing are not that great at emitting, and vice versa. But you can, they're similar material structures.
Could you, for example, create structures that absorb or emit infrared so that you could heat or cool the structure?
Yeah, you can get a lot of those. So they have these kind of heat-absorbing structures. So you do get materials that are really good at cooling structures. I think that's relatively trivial as far as I know. I think infrared is a harder domain for us to work in conjugated systems, because you have to get really bizarre molecular designs to push into that part of the spectrum. But I know they exist. In my head, if someone's making something that absorbs infrared light, they're generally trying to make an infrared detector. So something that can detect that infrared is there, rather than trying to make something that can kind of passively cool. But I don't doubt that someone's working on that. Whether they're working on that with conjugated polymer materials, I'm not entirely sure. But certainly, you get a bunch of chemists who are really, really good at designing molecules, and a load of physicists who understand how to characterize their properties. And then material scientists and engineers who can come together to say, this is how we put it in a technology. And you just have so much opportunity for innovation. And there's been some kind of cool work recently, both kind of from a quantum side, but also on using AI for materials design, but kind of trying to map out, take everything we've learned about materials design and functional properties so far. So you've got, all of literature that has all of the characterization that we've done of different material systems, put that into some kind of algorithm that then can predict how you design a better material system. So how do you optimize that? And then spit out this chemical structure that then a chemist can synthesize, so we can say, we want X absorption at Y wavelength, so now go and make Z molecule. And so I think now we're getting more efficient at doing that. Before it was a little bit trial and error, and now it's kind of computationally informed materials discovery, which is just really exciting.
And potentially, could you use that to generate things like, for example, plastics that would actually have a solar panel integrated into them or printed onto them somehow? Is that
100%? 100%. I think that at the moment there's, as I told you with the kind of LED story before, these devices are kind of sandwich-like structures. So as long as you can print the different layers of your sandwich, if you have a printer that can print the electrode at the back, the layers at the top, the layer of your active layer, the electrode on top of that, and then for sure you can integrate it into whatever, you can. I've seen these things printed on glass that then go and get used as windows that are transparent to visible light, but absorb in the infrared and the IR, the infrared and the UV, and then generate electricity with the UV and moderate the heat with the IR. So you can definitely get creative. And of course, if we had this, I've spoken a lot about getting physicists to talk to material scientists to talk to engineers, but actually if you had architects coming to talk to material scientists and engineers about what we can do now, you could design much more sustainable and, world transforming buildings where you're generating power all the time. And we keep the way that we want to live life, but actually you're doing it with your building is the smart thing in that aspect. So yeah, I think you could definitely do it with printed windows.
Well, that's super interesting because I think, as you know, one of the focuses of what I'm doing at Hyperlight Ventures is technologies that are driving sustainability in the property and finance sectors. And so, and a lot of that is new materials and new ways to build things. And I think you probably know that I've got a very strong interest in 3D printed construction and how that can be applied. So I do think that there's a lot of potential opportunity for the application of these type of technologies to create new products and new structures that we just innovative structures that don't exist today. And that has a huge potential to disrupt the property and construction industry. Jess, I just wanted to move on to something which is a little bit off science. I think my understanding is, and you correct me if I'm wrong, that your mother means a lot to you, and that she has been something of an inspiration for you for your interest in science and physics. Can you tell me a little bit about that?
Yeah, I guess both of my parents. My mum is great. My mum is a psychiatrist. My dad and my brother are neurologists, actually. And my mum, I think, taught me a lot about both my parents taught me a lot about working hard and particularly working for the greater good. I think I've grown up in a family of people who work for the NHS. So despite coming out of that not wanting to work for the NHS, I came out of that thinking I should do a job that helps people. I think working in a university gives you that opportunity to be curious and drive your own research in all of these peculiar and wonderful ways, but also to teach and to bring together communities of people. And now I work in an engineering department genuinely to take that kind of huge potential technological opportunity for systems that benefit society and the economy. And so I really genuinely feel that working in university is a huge privilege for that. And my mum is also just a fantastic transformer and supporter of people. And I think something I've noticed throughout my scientific career is, obviously this is probably exactly the same in investing, but people are much more productive when they're happy, and the importance of supporting people in teams and sitting down and we make much more progress when we work together on big challenges. So sitting down and not just listening to people, but actually hearing them and getting everyone on the same page so they feel valued by a system. I think my mum is incredibly transformative and amazing at that. And probably also I've grown up in a household of people who are very quick at taking a medical history, getting a lot of information about people quickly. I think I'm probably picked up and absorbed that. But yeah, my mum, throughout my childhood was my mum, my brother's mum, but also an academic and a clinical psychiatrist. She now works in student mental health, which obviously impacts a lot of what I think about because we have a lot of students at Imperial. But I think that commitment to working hard, but also having and looking after a family and having a life outside it is something that is remarkably inspirational. And I always thought I need to think about. Well, I always felt that motivation because she worked so hard to support us that I always felt that motivation that I should work so hard to make her proud. So yeah, my mum was a big inspiration. I think I didn't appreciate it until I was, at university. I just thought it was a bit unfair that she had to work so hard all the time. I remember when me and my brother were about 10, she went to a conference in Vancouver to speak. And we got so upset that she had to go. She went for less than 24 hours. She landed in Vancouver, did her talk, and came straight back. And I cannot imagine ever doing that. Or just, those things. And now I think how cool that she was doing that, then. But yeah, I suppose she's made me think a lot about what we can do to better support women scientists and women professors. And then just to open the door to more scientists and engineers.
Well, I guess, most people don't, end up working hard because they enjoy what they do. And I'm assuming that your mum was, she was committed to what she was doing, and so she worked hard at it because she felt it was important, but also enjoyed it.
Yeah, and it was this incredible time. My dad and her came to London to be doctors in the late 80s, and I think there was the AIDS epidemic, and my mum was working in mental health, and she did a lot of the kind of setting up needle exchanges. So we lived in Camden, and she set up all of these needle exchanges to protect people who were injecting with needles, so they had clean needles, not transferring AIDS using dirty needles. And it was so frowned upon at the time in communities who really didn't want to admit they had a problem. But actually it was so critical to get this right. So she was doing this really extraordinary thing, when I was really, really little, without me being aware of it at all. And now I hear about it. Someone emailed her about this time last year and said that she was the matriarch of the service. And I was just like, how cool is that? What an inspiring woman.
Yeah. And I think, it's interesting that what you said about bringing people together, and I guess particularly bringing people who think differently together. I think one of the challenges in venture capital, and I think potentially also one of the challenges in science, has been how you ensure that you get cognitive diversity. If you get a bunch of people from all the same gender or all the same ethnic background together, you lose something, because what you don't get is the different ideas that come from your different ways of life, and that cognitive diversity has immense value. You end up with more innovation. I mean, it's been proven by studies that you end up with significantly more innovation when you bring groups of cognitively diverse people together. And I think that kind of neatly sort of leads into the work that you have done on Wikipedia. What inspired you to start writing Wikipedia biographies for underrepresented scientists?
Yeah, I mean, I think exactly what you said. I think diverse teams of people make breakthroughs faster, and they come up with solutions quicker. And if ultimately that's what we're about in tech development, or if that's what you want in venture capital world, then we need diversity. Whether that's gender diversity, discipline diversity, diversity of roots. Something we undervalue massively are our research technical professionals. So people with technical skills who aren't necessarily on an academic track, who have huge amount of experience. Even I've been working recently on a few big proposals, and have been working alongside the most fantastic and supportive and incredibly intensive and diligent and creative administrative and HR support. And I think we massively undervalue that contribution to innovation, that you don't just want that disruptor who's out there for themselves and their own idea. You need those people who can support technically, who can provide really great administrative oversight. And we undervalue that from a diversity lens as well. I guess I started the Wikipedia project a few years ago. I'd been thinking about diversity in physics for a long time. Ever since I started physics undergrad, before I did a physics degree, I did an art degree. And going from being in art school to doing a physics undergraduate, you're just suddenly struck by how non-diverse it is, how pretty much physics recruits from male populations, from incredibly privileged populations. So most people who do physics at university, or a university like Imperial or Oxford or Cambridge, will have gone to a private school. So you're selecting from a handful of the elite to go there to study this subject, which, as discussed, physics is a subject that selects for a particular type of person. And because it does that, you don't have the diversity that you want to create a really disruptive technology. So actually something I feel quite passionately about and have done since my undergrad is how can we better represent the society we're trying to serve within a physics department. So I've done a lot of kind of outreach and working with high schools, really working with teachers and parents to change their perspective of what physics is. We have a huge challenge globally in recruiting really great physics teachers. Most physics teachers in the UK or the US don't have a physics background who are teaching kids. So most people will not have a specialism in physics when they become a high school physics teacher, because you can get such lucrative careers outside teaching. Why would you do a career that's so stressful and underpaid and undervalued? And so if you have that huge shortage of physics specialists, the majority of kids are learning physics from someone who probably doesn't even like physics. And then that, of course, impacts their perception of the subject and whether they go on to study it to like an advanced level. And so in high schools, which are already over-resourced and overprivileged, you're more likely to have a physics specialist teaching physics. So you kind of get this self-selection for the type of person who takes it, which impacts who studies it. And I guess that kind of inequity and unfairness just drives me crazy. So I've been trying to think about ways we can fix this and really trying to help teachers teach physics in a more inclusive and an exciting way. And then I kind of flipped the challenge on the head and thought, actually, we speak so much about the underrepresentation of women and particular groups within sciences. And what if we did a better job of just celebrating the ones we had? So alongside doing this work of kind of thinking about how we support more people to come in, I was thinking, how do we really champion and support the people who are already there in the system? And one of the ways in science that you do that is around kind of recognition and, you know, documenting who's contributed what to scientific discovery and understanding. Who do we give awards to? Who do we give prizes to? Who do we credit with the discovery or major breakthroughs? And I guess, you know, I try as much as I can to nominate people for prizes and awards, but also just to get them better reflected on websites like Wikipedia. You know, it's a phenomenal democratized platform for knowledge sharing. It's an incredible global project, Wikipedia. To imagine an encyclopedia which is entirely contributed to by volunteers, with this huge space in which it provides information in 300 different languages to people from all different walks of life. I just think it's a beautiful testament to humankind to have a platform like Wikipedia. But unfortunately, not everyone contributes equally. And so the content on Wikipedia isn't as diverse as it could be. And so, you know, when I started this project in 2018, about 17% of the biographies on English language Wikipedia were about women. Now I've been working on it for quite a while, and lots of other people have been working on it as well. And I've been writing all of these biographies about women scientists and scientists of color and other historically excluded groups. And it's about 19.5% women, which is a little bit better. But really, we've got to flip that narrative on, and it happens in so much of society, you know, kind of what we value, how we recognize excellence, how we define notability. And because Wikipedia reflects the biases of society. And if we keep undervaluing women's contributions, then unfortunately, these kind of platforms will keep under recognizing their efforts towards understanding the world.
Yeah, and I'm fully on board with the importance of it, and you know, I think particularly in both of the fields that we're in, that kind of cognitive diversity and diversity of ideas is really super important. Are you able to share one or two stories of scientists that you've written about that have particularly resonated with you?
I guess the most profound one that's kind of left the longest impact on me and from what Wikipedia can do was a phenomenal mathematician called Gladys West. She was born in 1930 in Virginia, and she went to a historically black college and university, and she's just 10 out of 10 sensational. So she's kind of 93, 94 now. She went to a HBCU. She ended up teaching maths in a high school. She then worked for the US Navy and did the calculations that enabled GPS. So she worked out how non-spherical planet Earth was. So you could put satellites in orbit around planet Earth and get a proper sense of position and therefore be able to do kind of navigation. She also did a lot for her local community. She's just an incredible woman. And I put up her Wikipedia page in February 2018. By May, she'd been nominated by the BBC as one of their top 100 women in the world. She was covered by pretty much every national newspaper. The US Air Force inducted her to the Hall of Fame. The Royal Academy of Engineering gave her the Prince Philip Medal and Prize, which they'd never given to a woman before in the history of the prize. So you kind of take the story of this 90-plus-year-old mathematician from Virginia and you put it on a platform where everyone can read it, and just they say, like, oh my gosh, we should have been recognizing her all along. So I think that's just an amazing, you know, credit where it's due, and at the right time for her to get it during her lifetime is just the most remarkable thing. And then just like in the pandemic, I became increasingly frustrated that every time you turned on the radio or watched the television, it was kind of a white male statistician or epidemiologist or public health doctor, when I know that doesn't reflect the public health or the epidemiology community. And so I started working actually with my friend Mariam Zarin-Garlam, who now works in the White House Office of Science and Technology Policy. And we were just making sure that all the particularly women of color were better represented on Wikipedia, so that almost from a public trust perspective, if you see those types of people leading efforts around vaccinology or epidemiology, you're more likely to engage or have a vaccine if you're from that particular community. And there's the most phenomenal woman called Kizzy Corbett, who's now a professor at Harvard, Kizzmekia Corbett. She was at Moderna, NIH, and developed that vaccine. She was then probably the youngest person ever, I think, to be appointed professor at Harvard. But she did all of the kind of engineering to make the mRNA vaccine for COVID. Phenomenal woman, and was nominated by Fauci for Time Person of the Year. So I like to think that Fauci or a member of his team read the Wikipedia page that I wrote.
Well, that's the thing, isn't it? If people don't know about other people, they kind of, they can't get recognition, can they? And so I think that's a really important piece of work. I'm thinking for that. For me, that's super interesting. And I think, it's a great accolade to you that you have, have made such a dent in, and made such a difference. And I think it's not just about the dent that you're making personally. It's about the inspiration that will create for other people to carry on and deal with that, and do that kind of work. And I think in many ways, one part of the vision that I have for transforming venture capital is about bringing much greater diversity into the field. And I think therein lies opportunity, because if you it's a form of competitive advantage in a way if you are able to have a broadness of thinking that escapes other people, because they are they come from a particular type of background or
I think
way
that's
of thinking.
It's how do you identify gap? How do you do a proper risk analysis or gap analysis if you don't have diverse teams of people doing that? It's like every one of those health apps that was developed without women on the leadership team and forgot to put anything in about women's health. Those kind of really dumb things where you just think, actually, someone could have said to the people who are developing all of these algorithms to monitor for prison populations or whatever they do in the US, and how they over incarcerate people from communities of color because they over police them because of the way that these bias algorithms are designed. If you had people of color within the team, then you completely stop that happening because they'd recognize that this was some kind of potential issue. So I think there's both that need for having diverse teams of people on the tech development team, on the company team, but also kind of ethics and responsible innovation in the way that we do our training, that we really don't do that at the moment. If you imagine a computer science undergraduate degree or a physics undergraduate degree, at what point do you talk about ethics, or what point do you talk about you can do this with this technology? The real question is, should you do this with this technology? And I don't think we do that at the moment enough.
I don't think we do it enough. It certainly does creep into some courses, and I know it's ethics has become a big part of most MBA courses now these days.
Yeah, so it comes in at postgraduate, but maybe not at undergrad.
Yeah, and it is important. I fully agree. Okay, jumping back to technology, one of the challenges that you and I have discussed is how to improve the connection between academia and business to help the commercialization of technology and to create the right incentives to fund further research. Could you just talk a little bit about the work that you've done in that area and what your kind of thoughts and vision are for where the opportunities lie?
Yeah, I think we're phenomenally lucky at Imperial to have an institute called the Institute for Deep Tech Entrepreneurship, particularly led by academic, a professor of financial economics called Ramana Nanda. But they're really doing this kind of, how do you bring together communities of scientists and engineers with fantastic ideas with teams of people who know how to create or how to de-risk a particular technology. Lots of these technologies that you would invest in or that we're creating are kind of those deep technologies where you need quite a lot of commercial investment to get to a prototype. You need a structure in place to be able to do the kind of rigorous testing and assurance and kind of reliability checks to make an investor come along with that. But as a scientist or an engineer, you don't know how to define those, right? Like, we don't have a phase 1 and 2 and 3 like a clinical trial. We've got to have those kind of fundamental testing blocks. We've got to design those ourselves. So actually the Institute for Deep Technology are doing that kind of tech development framework for these deep technologies, and also that kind of ecosystem analysis to understand what is it that scientists and engineers want from investors, what is it that investors want to understand about the science and engineering so that they feel more confident in investing in it. How does that map on to the infrastructure landscape that we have in the UK or the US? If I need to make X prototype, where can I go and do that in an accessible and affordable way? Because sometimes some of these infrastructure demands for these technologies are quite complex. and actually having open doors to those kind of capabilities and the technical expertise in them is really important. And again, bringing in that diversity piece, are we serving all of those communities equally? You know, is it that we're not funding women innovators? Is it that we're not better supporting Black physicists who come through with these disruptive ideas? So how do we make sure that we build equity into this landscape that historically hasn't been very good at supporting people from these different historically excluded groups? And so I'm really excited by that. I'm really excited by what we can do to better train investors and to build better partnerships. So we know when we're developing a technology, or when people from Imperial are developing a technology, we know what the investors want to hear and how we can best communicate that with them.
Yeah, well, and what's interesting, I think, is that in the kind of investment world, or in the venture capital world, or the startup world, there are kind of standard, templates or paths for moving a startup or a technology through to commercialization. And so I think, I'm looking forward to speaking to you more about how we can try and bring those two worlds together and actually help create opportunities for investment, but also create opportunities for commercialization of some of the work that's going on there at Imperial. So yeah, I'm very excited about that. Great. All right. Well, listen, I have really enjoyed our chat. We've covered a lot of ground. We've talked about a lot about different technologies. We've talked about diversity in science and in venture capital, and the importance of it. I think this is probably a good time at which to start wrapping up. Is there anything that we've talked about, or is there anything else that you'd like to say around what we've talked about just before we move to wrap things up?
No, just that I do think that we do need that kind of consideration, probably in investment and in science, but in all walks of life, that we need to do that part on kind of inspiring people to come into our sectors. We need to do that part on celebrating the phenomenal leadership we have, particularly from historically excluded groups, but really on trying to kind of keep people in. I think often we focus on those kind of two extremes of someone's career, but actually those times when you're kind of early on or trying to find your way, or thinking, how do I stay in this job in science when I'm not getting these opportunities? We really need to think about that kind of early career aspect of supporting people from historically excluded groups. And then something we didn't touch on at all, but I care a lot about, is working better with policymakers. And so how do we develop a kind of policy framework that supports, has a friendly, forward-looking approach to innovation, but is also doing the regulation, so we know we've got a sustainable quantum ecosystem or whatever, but actually also policy that allows investors to invest in these deep technologies in like the most supportive and de-risked manner.
Well, look, and I think one of the things that we could work on here in the UK is the sort of the feedback of, or the relationship between educational institutions and venture capital / startup investors. Certainly in the US, the major university endowment funds of the universities like Stanford and Harvard are strongly invested in venture capital, which is funding startups. So in effect, the research that's coming out of those institutions is being paid for by the investment that they're making in startups. The money that's going into that innovation is coming back and then funding more and more research, and that creates, I think, a virtuous circle, which we haven't really kind of cracked in that way in the UK yet.
I think
there's work to be done.
Yeah, I think there's kind of hints that people are going to start trying to go towards that direction. But I think you're right. I think we're really far behind what's happening in America. And I think you see that in the number of spin-out companies that are massive successes from UK universities. That we don't have that kind of Series B space of funding, but also we don't have that very clean pipeline for taking these disruptive ideas and then getting proper support to make them into a productive company. But I think we're getting there. We're definitely trying.
We are. Yeah, we're getting better and better. And, I think the way that I see it is that there's simply more competition for investment in the US. And so that does mean that the capital markets are a little bit freer, and that helps create more and more innovation.
That's a whole other podcast, I feel.
Yeah, no, you're right. And I think there's a lot for you and I to chat about there. Jess, it's been a real pleasure chatting to you today. if people want to find you, I guess they just need to search for Jess Wade at Imperial College. I mean,
they can just Google me. I used to be on Twitter all the time, but now that's a horrible place.
All right. Anything that, before we wrap up, anything that you particularly want to ask of people that listen to the podcast?
Come and talk to us at Imperial about thinking about disruptive quantum technologies or materials for quantum and the opportunities in that. And also, I think if you do think of ways that we in academia could better support investors to understand emerging technologies, we're definitely going to do some training around kind of quantum technologies for investors and AI, but other emerging technologies that investors think it could be beneficial to learn about, would be really happy to help support that delivery of that information.
Yeah, and that's something I think let's you and I talk about and see how we can work together on that. All right, Jess.
Okay,
well, listen,
awesome.
It's been a real pleasure talking to you today. Thank you very much for your time. It's a fascinating conversation, and I think I'm going to have lots to think about, and probably some more questions for you actually once
that's great.
Once I absorb everything you've said. So thank you very much. It's been a real pleasure, and I will see you again soon. Cheers.
Okay, bye.